So thank you to everybody. So I am Professor Nigro. We are from Roma Tre University. It's the third public university in the city of Rome. We are located in the southwest part of the city. If you would like to come to Roma Tre, for us, it will be a pleasure to host you. Now we will make a jump because we have talked about free transport, but now we are moving to travel demand, in general travel demand, and specifically about the importance of big data on travel demand. Because we know that we can speak about sustainability and measures, policies, but if we don't have a good knowledge of travel demand and traffic demand and what happens on our network, it's quite difficult to evaluate our policies and our measures for a better sustainability. This is a work that go ahead by about 3-4 years. Thus, there is a lot of story about this work. We are in the framework of travel demand modeling. Every one of you know that we can associate to travel demand an OD matrix, that is a matrix connecting origin and destination point, origin and destination zone of our, for example, city. And for each cell, we have the number of trips between the different zones of the city. When we move from the static case to the dynamic case, we usually deal with several demand matrices, one for each departure time. And it's quite challenging to estimate our travel demand. We usually teach to our students the 4-step models: generation, attraction, distribution, of choice. But it can be quite easy in some contexts, for example, for commuting trips. There are some scenarios in which estimating travel demand is particularly complex because the demand is quite uncertain. For example, for other motivation with respect to commuting trips, or for example, in other time of the day that are not the peak hours of the day. So how we can use all the data that now we have thanks to telematics. So let's come back to the first presentation. And how can we use this data to improve our estimation about travel demand? Which type of data, first of all? Maybe that you agree with me that when we teach to our students, now we are quite uncertain about if the problem is to calibrate models or to use data-driven models, because this is completely changed during the years. When I was a student, the problem was to calibrate our models. And now the problem is, how can we deal with all this data? Well, the first data that I would like to propose you are floating car data. Every one of us know that we can have information about probe vehicles moving on our road network. We call floating car data this type of data. And in the last years, there is a lot of a strong adoption of this type of data, for example, for estimating speeds, travel times, thus to derive condition on our network. But there are also some additional data. But now that I listened to your presentation about freight transport, I started to think, also how to adopt this new type of data, for example, for the optimal location of parcel lockers, or to locate depot for freights and so on. I am speaking about point of interest data that are data about the location of activities, and Google Popular Times that maybe you know when, for example, you search for a restaurant on Google and you see that there is a trend of visit patterns during the day. These are the Google Popular Times that can be both offline data or online data, and that can give us very strong information about the visit pattern of user in some activities. So how can we use floating car data? How can we use these not conventional crowdsourced data as a point of interest and Google Popular Times to improve our knowledge about travel demand? So we started to think how to use them, and we think specifically to the motivation behind the trip. I hope you agree with me that if we observe traffic flow on a network, this is the convolution of people making different activities during the day. So yes, commuting trips are fundamental, but in some other hours, we are dealing, for example, with leisure trips or trips for other reasons. So we started to think it is possible to understand better our knowledge of travel demand in terms of motivation behind the trip, because the demand is a convolution of motivations. So we started from floating car data, and we try adopting with different algorithms to understand if, for example, these trips are related to an home or work trip, that's commuting trips. But if we are not able to fix the origin of the destination point of the trip with a home or a work location, what else? I am going to the gym, I'm going to make shopping. So we are now focusing on not systematic trips, and we would like to understand if crowdsourced data, floating car data, together with point of interest and Google Popular Times, can give us information that permit us to define additional motivations. So as you can see by this flowchart, we are going to define non-systematic trip through the adoption of this data. How? Well, in this way. Let's have a look to an application directly. So we started to work with a subzone of the city of Rome. This is the EUR zone of the city of Rome. It is very close to our university, and we take all the point of interest of this zone, and we take the Google Popular Times of this point of interest, and adopting clustering techniques, we derive different visit pattern related to the point of interest we collect on the zone. Together with the visit pattern that are clusterized for this point of interest, we collect also information about the visit duration. That is another information that we can have with Google Popular Times. So we take our floating car data, we divide them in, okay, home work trips. So you can go inside a travel demand, a sample matrix related to commuting trips. You are not an home work trip. Let's have a look if there is a high probability that you go inside a specific visit pattern and visit duration. So we fix each trip with a specific cluster of activities. This is, in this case, a deterministic approach. So for each trip, we fix the most probable case in which each trip can be associated. But we started to have some problems. The problems are mainly two. One is that inside each of this cluster, for example, you can have also very different type of point of interest. For example, a restaurant together with a bank or together with a pharmacy. So we are not able to fix a specific motivation behind the trip, because after the clustering technique, it's not possible to univocally define a motivation of a subset of activities. So this is the first problem. The other one that you can see here is that we adopt a specific zoning system that is quite regular, specifically an hexagonal traffic zoning system that is very fine, detailed, with some zones that are very small in size. And when you deal with floating car data, that is a sample of your travel demand, you can have a sample matrix or different sample matrices that have a lot of empty cells. This is another problem. So the first question that we started to solve is, how can we deal with an optimal traffic zoning system in order to be able to not have all these empty spaces in our travel demand matrices? And the other question is, how can we solve this problem of univocally defining trip purposes? Because in each cluster we have very different activities. So I think that now we can start with the first spin-off of this research, that is how we can deal with an optimal traffic zoning system to reduce our empty cells in our OD matrices. And I will give you the floor to Marisdea for this specific topic. Thank you. Sorry for the change. No,
So I will talk about the second section of our presentation, which, as the professor introduced, it is about the definition of an optimal traffic analysis zoning system. So I want to stress the importance that the definition of a correct and useful traffic analysis zoning system means for everything that comes after it. So all our demand modeling, but also the supply models, strictly depend on the goodness of our traffic analysis zoning system. Because if we use zones that are too small or too big and not reflect the real necessities of our traffic study or study area that we are taking into account, or if our zones do not respect the physical barriers or the limits, the boundaries of our study and the area that we are analyzing, then the rest of the modeling will not accurately reflect, the real conditions on our road network. So we can consider traffic zones as the basic units of transportation models, which are representative of the spatial aggregation level that we want in our study. And this is strictly tied to the accuracy of our models after that. So usually, what do we do to define our zoning system? Firstly, we define
how many zones do we want? So we define the spatial level, the spatial aggregation level that we want, because depending on our study area, depending on the type of study that we want to conduct, we might need bigger zones covering a wider area, or very small zones to have a very detailed traffic model. Then after setting the spatial aggregation level that we want, we have to define, okay, then what shape will the zones have? How big will there be? And of course, we don't want zones that have the exact same dimension, a regular dimension, like for example, the initial zoning system that we adopted, the regular hexagonal zoning system we adopted. We want these zones to fit the real conditions of the study area. And in literature, this problem is usually formulated as an objective, as an optimization problem, where the objective function aims to maximize the homogeneity of these zones in terms of socioeconomic characteristics and mobility characteristics, while at the same time minimizing the number of intrazonal trips. So the trips that adopting this zoning system will have their origin and destination fall within the same zone. So we want to avoid that, as intrazonal trips will represent the information loss of our model. If we have a high number of intrazonal trips, this means we have a high percentage of information loss in our study area and in our model. Moreover, usually in specific applications, we just apply general guidelines, and the decision of the zoning system is usually left to the knowledge of the transportation planner of the area. So there's no strict procedure to follow, like an automated procedure to follow. It is left to the knowledge of the experts. Moreover, we have access, as we mentioned in the first section of our presentation, we have access to a lot of data that can give us a lot of insights about land use, about mobility characteristics, about activity characteristics of the area that we are studying. And a defined approach of traffic zoning system in a big data era does not exist yet. So we try to catch two birds with one stone. We needed a way to aggregate or very small fine-grained zones into wider, more coherent traffic analysis zones. And at the same time, we wanted a way to utilize the data that we already have. For example, the POI data from OpenStreetMap and also the floating car data. And we added a few more open data sources that I will go into it soon, in order to put together a model that allows to define an optimal traffic analysis zoning system, which leverages crowdsourced data and uses land use characteristics, uses mobility behavior characteristics, and features of the transportation networks. And all these types of information, we gather it from two types of open data, openly available data. So OpenStreetMap data and satellite imagery that you can find easily online. At the same time, however, we want to stick to the original point of traffic zone definition, so minimizing the number of intrazonal trips. And we do this using the same floating car dataset that we used in the previous application. So I will go more into the data that we used. We used OpenStreetMap data, and from this publicly available dataset, we can extract for all the zones, the basic units that we had split our study area into at the beginning. We can extract information about types of amenities in the area, area boundaries, number of buildings, as well as the area coverage of these buildings, commercial activities, both in their number and in the area covered by commercial activities, information about the road network, car-friendly road links, as well as non-motorized, like pedestrian and cyclist-friendly road links. And then we have to take into account, of course, physical barriers, such as, for example, rivers and waterways, such as the river Tiber here in Rome, or railways, anything that can diminish the accessibility of certain zones in terms of mobility through these physical barriers.
Then we integrated satellite imagery data obtained from the European Space Agency world cover data. This is an openly available dataset that has been released in 2021 and contains satellite imagery data at very high resolutions with high accuracy for a lot of the world. And contains 10 different land cover classes, which allow us to classify our zones, our basic units, within the built-up areas or the green areas, for example. So they're land cover classes. And lastly, we use the floating card data, which already went into. So we have GPS data from which we can reconstruct the origin and destination trips of the observed user. So we know exactly which user does what, anonymously, of course. We can reconstruct their origin and destination, and we can use them to assess the goodness of a model. So firstly, actually, there has been an evolution with the first basic unit. So we through image segmentation, we adapted our study areas. We split them into 229 basic spatial units. This can be any types of spatial units we can contain. We can use hexagonal regular zoning system. We can use image segmentation to obtain our basic units. We can use census particles to start from. This represents the smaller units, the smaller elements in our model that our models will aggregate based on the features we have extracted from the data. So we cover an area of about 100 kilometers squares here in the air district of Rome nearby. And then we use the dataset, the floating card dataset we have collected. So we have 1.5 million origin destination trips, which have been carried out along 4 months of 2020 from September to December. So the first step of our model is to select which features from our data actually matters the most for our study areas. This might change according to the objective of our study or of our study area. So in our cases, there are information about public transport facilities, about services in the areas, about number of buildings and areas built up, number of commercial activities, the total length of car-friendly road infrastructure and non-car friendly road infrastructure, so bike lanes and pedestrian streets, and then also the amount of green areas. And then using cluster, we evaluated a few initial configurations, so we used clustering techniques to put together the smallest basic units, even if they are not contiguous. Then if the zones were in the same cluster and were contiguous, they could be aggregated into the same traffic zones. However, if the aggregation of these basic spatial units are contiguous and are considered to be homogeneous in terms of the important features that we selected, but these zones, we did not form a big enough traffic analysis zones that contains, in our case, it had to contain at least 3 of the basic spatial units. So if wide enough for our study analysis, traffic analysis zones were not formed, then the rest of the basic spatial units were considered to be outliers that we had to reclassify in order to match them with the most likely configuration. So the most likely cluster, the most similar cluster. So we start an iteration procedure. I won't go much into the details of this procedure, but we, through iteration, we will classify all the outliers in order to aggregate these traffic analysis zones automatically. The second part of this model is to evaluate how good this aggregation is. And firstly, we consider the percentage. We assign the floating card data trips, destinations, and origin destination to the newly found traffic analysis zoning system. And we evaluate whether globally in entire study area, the number of intrazonal trips over the amount of trips that have destination in the area surpass a certain threshold. So if the percentage of intrazonal trips is high, it means the initial configuration where ready to aggregate it. So we restart the procedure using a larger number of initial clusters. However, if the global threshold is fine, then we will go into the evaluation of the specific. And for each specific zones, we want that the ratio between the number of intrazonal trips and the area of that zone doesn't surpass a certain threshold. In case it does, we can split the specific zones where we have a lot of intrazonal trips into further zones using the same methodology. So this was a presentation on how we use the same data that we used before. So OpenStreetMap or floating car data in aggregation with in satellite imagery in order to obtain a more coherent and a more suitable traffic analysis zone system for our study areas and for the objective of our study that allow us then to have origin destination matrices, sample origin destination matrices that we can use in the further section of our study that is not as sparse as before, as every section of our origin destination matrix is filled with the floating car data trips. So we can go within the third section of our presentation.
We can see this way. Yes, I will introduce the second challenge. As I told you, the problem was to uniquely define the trip purposes, because in our clusters of point of interest, we have inside very different activities. But we think to solve this problem, moving from the definition of trip purpose to the definition of the flexibility behind the choice of activity, behind the choice of our trip. I mean, how much is flexible in time and space a trip that I perform, for example, for working, and how much is flexible a trip that I would like to perform, for example, for going to the cinema. So we change our point of view and we modify a little bit our framework, also using some famous works in the literature, and specifically the work of Doherty in 2006. We use his classification of activities in macro activities. Some of them are mandatory, some of them are more flexible. For example, that it means that we have a lower priority, both in terms of time and space. So we decided to divide our point of interest in different macro activities following the definition of Doherty. And once that we define these macro activities, let's have a look. For example, in macro activity 3, we have all the points of interest related to stores and supermarkets. So we define a priori what is macro activity number 3, or for example, macro activity number 2, sustenance, that means restaurants, bars, and so on. So we firstly, taking the point of interest, we put inside each macro activity, and then using the clustering technique for each macro activity, we define the visit pattern and the visit duration of all the point of interest located in these macro activities. In this way, we are able to define in a stochastic way some probabilities. There are the probability to arrive in an activity in a specific time interval, the probability that the point that I would like to visit is related to that specific macro activity, and the probability that my stop has a specific duration in time. In this way, I can assign each floating car trip to a specific macro activity. Remember that each macro activity needs a specific flexibility in time and space. This is fundamental because I can then associate to each sample matrix for each macro activity some important information about my travel demand that are, for example, the departure time, flexibility. So how much I can change my departure time, how much I can change my destination, or think at least I can also decide to remove my trip if it is more flexible. Okay, how can we use all this kind of data? And I give the floor again to Maristea, but I would like to say some other words to you. When you use floating car data, you always rely to sample OD matrices. I mean, it is not the travel demand, it's a sample. So if you would like to go to the travel demand, you have to expand your sample matrices to the whole population. How can we move to sample matrices to matrices related to the whole population? Well, we need to go to some instruments that you already know. For example, the travel demand adjustment process. I hope that every one of you is familiar with travel demand correction based on, for example, traffic counts. Well, now we have a lot of data and we have estimated flexibility in time and space. Thus, there is the possibility also to adjust the traditional correction methods in order to take into account this flexibility in time and space.
So from the previous approach that has been presented just yet, I wanted to recap, okay, what are the two main things that we have obtained? What are the two main insights that we have obtained from our crowdsourced data? And the first thing is, of course, various number of sample origin destination matrices, which will represent trips from one destination within a certain time interval for a specific component of travel demand, which represents our previous macro activity. So a component of travel demand that is characterized by a given spatio-temporal flexibility. Moreover, for each of these travel components, we have a very reliable estimate of the variability of the departure time choice, for example, of the variability of their spatial location choice. I'll go very quickly. So what do we do? What can we do with this? We can integrate our data-driven model, our data-driven insights with traditional models, traditional travel demand models. And in particular, we propose an approach that is a direct extension of traditional generalized least square models, where the objective is to minimize an objective function that takes into account the difference between traffic counts and the influence obtained from assigning historic seed matrix over the road network, and then minimizing the difference between this seed matrix and the matrix that we are estimating and that we want to obtain. However, we can simply extend this objective function by including a number of different travel components. However, this means highly increasing the number of unknown variables into our problem. And as we know, this problem is an already very complex problem in terms of computation complexity and in terms of the high number of unknown variables compared to the number of data that we have on the road network, so traffic count. So we needed to find a way to exploit the insights that we gained about travel flexibility, spatial temporal flexibilities for each of these travel components, to integrate into the regional model in order to not increase the complexity of the model, while also taking account the different flexibility. So I won't bore you with all the formulation stuff. I will just explain what we aim to do. So we define each component, each travel demand component, as a product of the prior probability of the single travel demand component that we have obtained from the classified floating car data. So we can define each unknown variables as the product between this prior probability and the actual variable that we want to estimate. So the demand for each origin destination pair and for each timing. So we don't increase the number of unknown variables, on our problem. Then we use the same gradient descent algorithm in order to optimize the problem. And however, at each iteration, we insert a new phase, which is called demand components adjustment phase, which each demand component is adjusted through a maximum likelihood estimation problem that is constrained. What are these constraints? I will try to give you a visual explanation of what these constraints are, both in time and phase. So for example, if I go to work at 8 a.m., I'm supposed to go to work at 8 a.m. each morning. I will have very little flexibility in terms of how much earlier or how much later I can depart from my house. So we'll go at 7:45, for example, or at 8:15. However, if I go grocery shopping, the flexibility of my departure time is much wider. At the same time, in terms of spatial flexibility, if I go to work, I will probably have just one location to choose from, maybe two, but mostly one. However, if I go grocery shopping, I will have a plethora of options to choose from. We can translate this into the constraints of our maximum likelihood problem it is the pictures at the bottom, where we can consider these constraints in terms of spatial temporal flexibility, in terms of how wide these blocks on the origin destination matrix is, and how much overlap there is in these blocks. We mean that travel components that will be more rigid, such as going to work, will have very tight, very overlapping blocks, whereas more flexible travel demand components, such as shopping, for example, will have wider, less overlapping blocks, meaning this travel demand component is less constrained and will be able to vary more compared to the more rigid components within the adjustment of our demand matrix. So we applied this model to the same study area. We conducted first a lot of experiments on a toy network, but then I will show you directly the application on a real network. This has 54 traffic zones, meaning almost 3,000 origin destination pairs, so almost 3,000 variables for each time interval that we are considering, and only 8 traffic count detectors on the area. So we want to show that including additional information about the flexibility and the demand components, the distribution of the demand components in our area can improve applications where traffic counts data or other types of traffic data is scarce. So this is the application. We classified our floating car data trips. This is the spatial distribution of all our trips, and we have classified them into home, the red dots, and work trips, which are the blue dots. And for each of our traffic zones, we computed, okay, how many home trips there are over the total amount of trips that have destination in the zones. How many work trips there are that have destination in the zones over the total amount of trips. So we computed this fraction for each zones. And then the others, through the previous section through the model that we introduced in the previous section, all the other trips have been classified according to their spatial temporal flexibility, and the macro activities that we obtained from the previous model. For each traffic zone, we have computed the percentage of each trip for each macro activity for each zone. And we put this into our model, and we did a lot of tests comparing traditional GLS model to this new Flex GLS model, which is a boosted GLS, which extends the original model to different travel demand components and is constrained by the information that we gained from ThroughCrowd-sourced data in terms of spatial temporal flexibility. And as in the result here, I will just go quickly over it. We can observe that both in terms of estimation of the overall demand and overall replication of traffic flows on the network, the Flex GLS performs better of GLS when reliable insights about demand components and their flexibility is fed into the model. Moreover, a more reliable estimate of each individual travel demand components can be obtained through Flex GLS, which the traditional GLS model simply cannot do, since we only consider one single travel demand entity. So to finish our presentation, maybe the professor wants to add something.
I think that we spent a lot of time with this presentation, and I don't know if you have some question, maybe that was okay.
Yes, I have one question. So can you say me please how can take into account the chain of trips if we have regular trips and non-regular, and we have some different purpose of our trips?
Okay. Well, these are two different questions. I mean, for example, home and work, we work a lot on the number of overnight stays. If the destination is has a certain frequency during the week, during the weekdays, in these terms, we try to define the home and the work. About the chains, and this is a very interesting point, because in this presentation you see a trip-based approach. I mean, point to point. We try to fix some short trip and try to correlate more trips when there is inside a short trips. I mean, for example, I go to school with my son. I stop to the bar and then I move to the work. This means that we join this type of trips, and it is then considered as a home to work trip. But in this case, we don't work with trip chains because this is a trip-based model. When we deal usually with odd matrices, deal with trips. You can work a lot with floating card data in order to there is a lot of research on this.
Maybe one last question, because we are already one short question, yes.
Short
question. Yeah, sure. Maybe from the line.
Then, okay. First question I delete. Second question. Tell me please, how reliable is the use of floor carbon? Understand?
Yes, we understand the question. Yes, it's a usual question. I mean that every time that we try to publish some papers using floating card data, it's a common question by reviewers. Well, we know something about our floating card data in the city of Rome, for example. The penetration rate. It means that we know that it is about 6% of the penetration rate with respect to the world population. We also perform some investigation about them in terms, for example, of population between different zones of the city. So if there is some zones that are not covered with respect to others. Of course, the reliability of the data is the first thing that we have to do when we started to work. Yes, there is a word. And I am most afraid about Google Times with respect to because Google Popular Times are evolving in time. And we expect to have always more data on them. So this is the beginning, but we start to push our models more and more as the data will become more relevant. Let's think to as a modeling framework.
Yes.
The data.
Got a question from
There
online?
is
Last question.
Thank you. It was really very interesting presentation. And with respect to traffic analysis, actually, I do have two questions related with one in favor of the conventional traffic analysis zone definition and in favor of related to like there are literatures which support the irregular pattern of defining traffic analysis. It's better because it is easy for us to get population data, socioeconomic data. When you make your like the regular regime, like sub-analysis, how you reconcile it. And the other is major darkness of traffic analysis unit. And I am worried, as usual in most of the aggregation cases, there is a multiple area unit problem. Have you checked any accuracy?
today. We lost the last.
The last question. Okay.
The last word. Have you
Modifiable area unit problem.
if we make a comparison between
Like the issue of the scale, like if we generalize some result with respect to like small areas, it cannot be generalized to the bigger areas.
okay.
And like
Okay, so if we move, for example, from the air network to the city of Rome, so if some problem about the scale of the, well, at this moment, what we make with the traffic zone definition is to compare the results of our model with some standard traffic zones usually adopted, for example, by the mobility agency of the city. It's quite difficult to make a perfect analysis because the zones are different. But we try to understand, for example, if the average dimension is approximately the same, is the average number of zones with respect to standard and manual zoning made system, it's quite similar to ours. So we try to work on this aspect to evaluate the goodness of our model.
Okay, thank you very much. Now we have finished this session.